Welcome to this tutorial session. I hope you can see my screen. Okay, so this is tutorial 4. So we are going to cover few questions based on what is being taught in week 4. Okay, so in this week, I think second order system was covered entirely. Okay, so I'm going to cover few questions on that based on second order system and based on the controller what are the transfer function and what of the popular controllers like a proportional integral derivative or proportional integral. Okay, so I have total 15 questions for this session. So first I'll go through what is covered in the week 4. Okay, so just a brief explanation. Okay, before solving the question. Okay, so in the previous question, in the previous weeks, we have covered up to first order system. Okay, so in the week 4, we went into second order system. Okay, so what is second order system? So if you see this ODE, okay, so this is the ODE, right? So if you see the degree, second, okay, so that's why it's called second order system. So this is ODE with constant coefficients. So if you get the transfer function by assuming all the initial conditions to be 0, you'll get this transfer function. So it's very like if you see the second order system transfer function, you'll get this in this form. Okay, so what is important is this denominator, which is also called the characteristic equation. Okay, because that's where you get the poles of the transfer function. Okay, so based on the poles where it lies, so our system is defined into categories. So these categories are like underdamped, overdamped, and critically damped. Okay, so based on where the poles of this characteristic equation lie. Okay, so based on that and how to decide. Okay, so underdamped, basically we are also linking our poles with the damping ratio. So zeta is the damping ratio. Okay, so if zeta is between 0 and 1, okay, so it is when it is between 0 and 1, you'll find that the poles of this characteristic equation will be lying in the S plane, right hand side, left hand side of the S plane. Okay, but not on the real axis. Okay, so if you see only this part, okay, the real part will be negative. Okay, and the other part will be imaginary. Okay, so like, so these are the two poles of the underdamped system. Okay, so what is the characteristic of that underdamped system that we have discussed? Okay, and again, if zeta equal to 1, zeta equal to 1 means both the poles lie at the same location. Okay, in the left hand side of the complex plane. And again, if the system is overdamped, we have both the poles and one is lying, and both the poles are lying on the left hand side. Okay, so based on where the location of the poles are, we have defined our system. Okay, based on zeta also. Okay, so looking at the underdamped system. Okay, so we try to find out what is the response for the uh, step uh, unit step function, right? So based on that, so this is the input, this is the output of that. Okay, so if you plot this output, how this output will look like, it will look like this. Okay, and if you see what is the input is this, and the red one is the output. Okay, so we want to achieve the output. Okay, so what does underdamped system does? So it will achieve the output. Okay, but it has some oscillation. So you can see this oscillation. So this is underdamped system. Okay, this is underdamped because of this oscillation, and we have defined some performance specification for this particular system, for the underdamped system. Okay, first is the rise time. Okay, so rise time is this, the time duration when it reaches 100% of its output. Okay, so this duration. So that duration, and you have to remember this. Okay, second order system, pi minus beta by omega d. So what is beta? So you can define cos beta equal to zeta. So zeta is the damping ratio. Okay, so you have to remember these formulas. Okay, so while we are doing questions, we also will be using these values. Okay, so what is happening actually? If you increase the zeta, what is happening? If you increase the zeta means you are increasing the damping of the system, and if you increase the damping of the system, your time increases, right? Damping means like this is for a let me give you an example here. Okay, for a particular damping ratio, this is the response that is shown here. Okay, so this is the response. So if you increase the damping, again what will happen? Your response will become sluggish like this. Okay, and if I further increase the damping, how the response will be? So your oscillations will decrease. Okay, your oscillations will decrease, but your rise time will increase, right? Because it is going to the uh, value of the input, that is 1. Okay, so it is taking longer time to get to that value. Okay, so again we have defined peak time also. So this is peak time. Okay, so peak time is this time. Okay, so when it reaches the maximum, right? So that's what the peak time is. Okay, so this value you have to remember, TP equal to pi by omega d. Okay, what is omega d? Omega d is natural frequency into 1 minus beta square. Okay, because these things we'll be using, so you have to remember these formulas for the second order system. Again, what is the maximum overshoot? Maximum overshoot is this. Okay, so what is its value? So how we can derive it? You can derive from this y of t. Okay, so just differentiate it. Again, that is covered in the lectures. So if you differentiate it, okay, you'll get the value of this time period TP. So again, you have to remember that that is equal to this value. So I'll just shade this. Okay, so this formula you have to remember for the maximum peak overshoot. Okay, first overshoot. Again, what is the settling time? Okay, settling time is this time. Okay, so when your output reaches within 5% or 2% of the that band. Okay, so this is the small band. Okay, so this can be 5% or 2%. Okay, so if you take the 2% band, so your settling time will be 4 by zeta into omega n. Okay, so you can derive this value also. So how you can derive it? So let me tell you, I think this is not discussed in the lectures. Okay, so you can put like y of t, you can put, okay, y of t, because this band is like 2%, right? So you're finding the overshoot, right? You're finding the overshoot. So let me zoom here. So what is happening here? Okay, so I'm just zooming this portion, right? So what is happening? Okay, so this is your band. Let's suppose this is your 2% band. Okay, and what is happening? This is the one value. Okay, so at infinity, your output will be reaching to this value. Okay, so what is happening? Your output is like this. Okay, it will decrease. So I will just show this. So it will be achieving this one value. Okay, so this is 5% band. Okay, let me do for 5%. You can do for the 2% also. So this is the 5% band, right? So what is happening? You can find this value. Okay, this overshoot. This is also overshoot, right? In the first peak overshoot, you're finding this one, right? So this was the first overshoot, but I have zoomed at the steady state. So you can find the overshoot at this place also. Okay, so this plus minus 5%. So let me not confuse you. So this is like whatever this is. Okay, let me just, so this one. So let's take this as 5%, right? Plus 5%. Okay, so how we can do it? You can y of t minus y of infinity. Okay, by y of infinity. So okay, this should be less than 0.5%. This is 0.05. Okay, that's how you have to find, and you can find the time period of this. Okay, so because you want to find time, right? Because y of infinity is what? Y of infinity will be equal to 1, right? So you have to find ts minus y of infinity by y of infinity, which is less than equal to 0.05. Okay, and then what is y of ts? Okay, so this is y, right? This is y ts, and if you put y of ts, what will be 1 minus, again just replace t with ts and solve this. Okay, for this particular, if you solve this equation, okay, so let me highlight, if you solve this equation, okay, you'll get the settling time for the 5%. Okay, so what is that? Directly they have written, which is equal to 3 by zeta into omega n, right? Any doubt how to calculate this? So that was not covered in the lecture. I just showed you how you can get this 4 by zeta into omega n for 2%, and uh, again 3 by zeta into omega n for 5% band. Okay, that's how you get the settling time. Okay, so again there in the lecture it's covered about the controller also. Okay, what are the type of controller and all this. Okay, so basically they have covered on off controller. On off controller is like it has only two output values, right? If error is less than particular value, okay, if less than particular value, the output of the controller is equal to u1. Okay, and if otherwise, if it is something else other than, if it is greater than e1, you'll have e2, only two values. Okay, so but in the practical scenarios you'll not be using this on off controller. So in control system, the popular controllers that we use is PID type of controllers. Okay, so we can use individually proportional controller, integral controller, or we don't use derivative controller, but proportional controller or integral controller. Okay, and also we can club them together, like PI we can use, PID we can use. Okay, so here they have shown the transfer function. So for the proportional controller, you have to remember this transfer function. Okay, this is very important. And for the integral controller, what it is doing, and this is the control block diagram for the controller, right? So E of S is the input, so this is the input, and U of S is the output, right? Output for the controller. Okay, so that's why the transfer function will be in terms of US and E of S. E of S is the input and U of S is the output. Okay, so if you see the integral controller, what it is doing, it is integrating the error over time. Okay, so if we take the Laplace transform, you'll get this. So you have to remember this, right? Ki by S, E by S. Okay, as you can see, in denominator it has one S, so it has one pole, right? Okay, so again another, so you'll see like what is now you're studying the controller, but you'll see what are its effect once you decide to combine this controller with the transfer or plant. Okay, that plant transfer function. Okay, again is the derivative controller. Okay, so it has 1 0, but again what it does, okay, it just amplifies the low frequency signal. Okay, that's what it is shown, that's why it is used with a low pass filter. Okay, that's what it is shown here. So its transfer function, if you see practically, derivative controller doesn't look like this. Okay, so this is practical. Okay, that's how KDS by TS plus 1. Okay, that's how we use it. And again, if you club proportional integral controller, so this is the equation, and if you take the Laplace transfer, you will get Kp plus Ki by S. Okay, so again, it's again we'll be using mostly PI controller and PID controller will be using for the practical application. Okay, so that's why these controllers are very important for the study. Okay, so again the proportional derivative controller. Okay, so that's how it is. Okay, proportional integral derivative. Okay, so again we are combining on the type of here controllers. So this is PID controller and its transfer function is looking like this. Okay, so we have seen like for a particular transfer function, if we add different types of controllers, how the closed loop system should look like. Look, okay, so in this is very important question. So if you see the PS, plant transfer function, is already unstable because it has, if you see the denominator, s minus 1. Okay, so this is the characteristic equation. It's, and the pole is lying in the right hand side, so this plant transfer function is unstable. Okay, but if you see, we are using a proportional controller, and if you find the closed loop transfer function, okay, for a particular value of kp, this closed loop transfer function becomes, okay, stable. Okay, so that's what the controller also can do. It can also stabilize the plant also. Okay. Okay, so based on like which controller we have to choose, okay, that we have to see what we can do about the transfer function. Okay, so that's what different plant transfer function is there, and we have to choose different controller. Okay, so that first the stability is met. Again, after stability, we'll go to the performance. Okay, so that's this is up to week 4. Okay, so any doubt in this? Anything? Week 4 theory. Okay, so important thing is you have to like at least memorize this proportional controller, integral controller, and derivative controller. Okay, it's transfer function if you are new here. Okay, and this specification, performance specification. Okay, so settling time, maximum peak overshoot, and peak time and rise time. Okay, so they're very important. Okay, okay, and this one, second order system, because for the second order system you'll encounter this characteristic equation multiple times. Okay, so you have to remember this. Okay, so we'll go to the questions. Okay, so I'll be solving the question. You just see the steps. Okay, in case you have any doubt, you can ask me. Okay, so anything. Okay, I'll read the question. So initial questions are simple. Okay, based on second order systems. So second order system is governed by this equation. So you have to find out for this equation whether the system is under damped, over damped, undamped, or critically damped. So first, let me write the equation. So this equation, you have to, if this is second order equation, then your zeta should be between 0 and 1. Okay, so that is one thing. So let me first take the Laplace transform with the initial condition equal to 0. Okay, so this is, so y of s is equal to u of s by s square plus 4s plus 2. Okay, so ps is what? ps is ys by uf s equal to 1 by s square plus 4s plus 2. So this is the transfer function for the plant, right? And how to find out whether this particular system is under damped, over damped, or critically damped? Okay, just see the characteristic equation. Okay, so this is characteristic equation. Okay, so you have to remember this equation, like, okay, for second order, general second order characteristic equation. All right. See, characteristic equation is this. Okay, so you have to compare with this. Okay, so if you okay, so the easiest thing is what you can do is you can find you can compare the coefficients of the characteristic equation with the general second order characteristic equation. Okay, so this is s square 4s plus 2. Okay, so you know omega n is, omega n square is 2, omega n will be root 2. Okay, and also if you see 2 zeta omega n will be equal to 4. Okay, so I'm just comparing these two equations. Okay, so let me just mark it with different pen. So this is, let me say it is equation 1. Okay, so not like this. So s square plus 4s plus 2 equal to 0. So this is equation 1. Okay, and this is equation 2. Okay, so I'm just comparing equation 1 and 2 and writing out these values. Okay, 2 zeta omega n is 2, and you know omega n is root 2 equal to 4. So zeta is 4 by 2. Okay, so this will be what, root 2. So zeta, this will be like 1 point, I think 41. Root 2 is what, 1.41 or 1.4? Okay, I think it is, I think 1.14, I think. Okay, so anyway, it is greater than 1, right? So this root 2 is greater than 1, right? So that's what we are interested in. Okay, okay. So 1.414, I think. Okay, thank you. So root 2 is 414, right? Okay, so this is, so let me write the exact value, 414. Okay, so which is greater than 1. Okay, so this is over dam system, right? Another thing is, what you can do is, you know, this characteristic equation like s square plus 4s plus 2. Okay, this you know. Okay, so what you can do, you can find the roots also. Okay, so all the roots you can find, minus 4 plus minus b square is 16 minus 4 1 into 2 by 2. Okay, so s1 will be equal to, I think it will come minus 2 plus minus root 2. Okay, something like this will come. Yeah, I think one root will be this plus, and s2 will be minus 2 minus 2. Okay, this you know. Okay, this will be the roots, right, of this particular characteristic equation. And if you plot them, okay, so this is s plane, right? So we'll get some here. Okay, so these are the two roots, right? And we know if roots are lying here on the left hand side plane, okay, this is imaginary and this is real, and it has imaginary part also, we'll say the system is underdamped, right, by seeing the roots also. Okay, though we are finding out zeta. No, sorry, this is not actually, the roots are lying here. So here. Okay, on the real axis. Okay, so that's why, and this will be omega and root 2. Okay, so you have studied, this is s1. Okay, this is, I think I'll just mark it s1 and s2 differently. Okay, which one is, okay, this is s1, this is s2. Okay, s2 is more negative. Okay, yeah, so if you see these two roots, okay, so they are lying on the negative real axis. Okay, both are negative. So you know, if roots are lying like this, okay, we say the system is overdamped. Okay, okay, so any doubt in this question? You have to find out the whether the system is what. Okay, based on the transfer function. Okay, so I have derived the transfer function, then I'm comparing with the characters general second order characteristic equation. So I got omega n equal to root 2, then zeta is coming out to be root 2. Okay, 1.414, which is greater than 1. That's why the system is overdamped system. Okay, and if you find the roots also, they will be lying here on the negative real axis. Okay, Any doubt? Okay, next question is second order system is governed by this equation. Its natural frequency is, okay, so this is second order system. Okay, so taking the Laplace transform, so we'll directly write the transfer function. Okay, this will be equal to 1 by s square plus 3s plus 9. Okay, so what I told you to remember the general characteristic equation second order. Okay, I'm writing this again once more so that you remember this characteristic equation, which is s square plus 2 zeta omega n s plus omega n square. Okay, because you have to compare the every other second order characteristic equation with this general equation. Okay, that's why you just remember this equation. Okay, so just compare. So in the question we have been asked to find out the natural frequency. Okay, so omega n is natural frequency. Okay, so if you compare these two equations, what you get, omega n square will be equal to 9, right? And if you find the root of this, 3, right? So it will be radians per second. Okay, this was very simple question. You have to find the transfer function from the equation and just compare it with the general second order characteristic equation. Okay, and if you compare it, you'll get omega n equal to 3, and you can find the, I think in the next question we have to find out, if you see, damping ratio, right? So how to find the damping ratio? Okay, again you have to compare the coefficients for s. Okay, so 2 zeta omega n will be equal to, so if you see this, 3, right? 3. Okay, so just now we have calculated omega n, so which is equal to 3, and we calculate which is 1 by 2. Okay, 0.5. So any doubt in second and third? Very simple. Okay, very simple transfer function is given, and you have to just compare with the general second order characteristic equation. Okay, so that's why I remember this. Every other second order system has to be compared with this equation to find out the natural frequency and zeta. Okay, so what we can say about this, zeta is coming out to be 0.5. So this is under damped system, right? So it's not asked whether what type of system is, but by looking at the value, you can say it is under damped system. Okay, so if you find the roots, you'll find roots somewhere here, right? So it will have imaginary part. Okay, so this is like two roots, s1 and s2. Okay, okay, so I think I hope there is no doubt in second and third question. They're very simple questions. Okay, so in case you have any doubt, you can ask. Okay, so I'll cover this fourth question. The frequency of oscillation in the unit step response of the system given in problem 2 is, okay, so how to do this? Frequency of oscillation. So the transfer function is given, right? Let me again write this transfer function, which is 1 by s square plus 3s plus 9. Okay, so this is y of s by u of s, right? Okay, So for the unit step response, you have to find the unit step response. So y of s is equal to u of s by s square plus 3s plus 9, and unit step. So what is the Laplace transform for unit step? 1 by s, right? So already we have covered in the previous weeks. Okay, and you have to find this. Okay, so already, so if you go to the lectures, so this is the same thing that we are trying to find out. Okay, so your response will be something like this. So let me write the response. Okay, so your y of t will be something like this: 1 minus. So for this particular case, let me write coefficients here: a minus b something b. Then I think, okay, you will have again this term, okay, and cos omega t. Okay, so a and b are not known, because if you try to solve this question, solve this for a and b, you can get this. Okay, so let me say how to solve this. Y of s, again you can write this a by s plus bs plus c by s square plus 3s plus 9. Okay, if you get abc, you can write a by s plus bs by s square plus 3s plus 9. Okay, plus c square plus 3s plus 9. Okay, so here you will get cos term, right? So I'm not solving, I will just say, I'll say this, you will get cos term. Okay, this you will get sine term. Okay, so it will be in this form. Okay, so I think a you will get 1. You see the equation. Okay, I think, okay, a you will not get 1, a you will get 1 by 9. So I'll just change this, so I'll write a here, a, this you'll get some b coefficient. Okay, and c you will get something like this. Okay, if you try to solve this abc y of s. But what we are interested in, again, this question, frequency of oscillation, right? So frequency of oscillation, so if you see this equation, this equation, okay, so if you see these two terms, right, oscillations are coming because of sine and cos, right? Okay, these two values. Okay, so these are responsible for oscillations, right? Okay, and sine and cos terms are responsible for oscillation. And what is the frequency of oscillation? Okay, so that oscillations is omega d, right? So this is the frequency of oscillation, right? I'm just saying, because we know this y of t, again, the longer ways solve this equation. Okay, abc you'll get. So without solving abc also, you can get these values. Okay, so let me show you the simplest one. So frequency of oscillation will be equal to omega d. Okay, and that is equal to omega n into 1 minus zeta square, right? Zeta is less than 1. okay, which is equal to 0.5. Just now we have calculated in the previous question. Okay, so frequency of oscillation is asked in the question for the unit step response, right? Which will be coming out to be omega d equal to omega n into root of 1 minus zeta square. Okay, everything is known to us. So this is 3, this is 1 minus 0.5, this is 1 minus 0.25, 3 into 0.75 root. Okay, so again this will come out to be 3 into I think 0.66, 2.59 or 2.6 radian per second. Okay, so this is the frequency of oscillation for a YT, because you know in YT which terms are causing oscillation, right? You have to see. So E, this is like exponential terms, right? So let me highlight those exponential terms. So these are exponential terms, right? So they will not cause oscillations. So only sine and cos terms will cause oscillation. Okay, and the frequency is what? Omega d. Okay, so you know how to calculate omega d, right? Directly. So I've calculated. So if you don't want to use the formula, okay, so I'll start from here. Okay, y of s. Okay, so suppose I don't know this. Let's calculate from. So you'll get a by s. Okay, so this is bs plus c s square plus 3s plus 9. Okay, so what you'll get a by s, this will be bs square plus 3s plus c s square plus 3s. Again, I'll not solve for ABC, but I'll show how to calculate the frequency. Okay, so a by s, so b, so we'll write in terms of s square, or you can write s plus 3 by 2 s square plus 9 minus 3 by 2 square. Okay, so I'm trying to get in this form. So let me write. It's like s plus a square plus b square, something like that form. Okay, because you know that its roots are lying on the imaginary axis, right? So that's why we have to make this change. Okay, so what I have done, how s plus 3 by 2. Okay, so divide this s part by 2. So let me show you, divide the s part by 2. Okay, which is 3 by 2 square, and again 9 minus 3 by 2 square. Okay, so if you solve this, you'll again get back to this. Okay, similarly we do for the other thing also. And again, what you can do here is s plus 3 by 2 and minus 3 by 2. Okay, similarly for the other one we can do s plus 3 by 2 square plus 9 minus 3 by 2 square. Okay, c. Okay, okay, so you can write in this form a by s plus b s plus 3 by 2. Okay, s plus 3 by 2 square plus 9 minus 3 by 2, this is whole square. Okay, and this you can write plus c minus 3 by 2 b, right? I'm just taking all the constants there. Square plus 3 by 2 square plus 9 minus 3 by 2 whole square. Okay, so just you don't have to calculate ABC. Okay, so you have to take the inverse Laplace. Suppose ABC are some values, right? So how to take inverse Laplace? Now you take inverse Laplace. Okay. So what you will get, this will be a, right, plus, you're not concerned about the coefficients. Okay, so what you will get, a b e raised to power minus 3 by 2. Okay, and cos, okay, you see this is cos, right, and 9 minus 3 by 2, this one. Okay, and you have to take the root into t. So let me just write, so I'll just tell you like why I'm writing like this. Okay, and plus c minus 3 by 2 b, you get sine root of 9 minus 3 by 2 whole square into t. Okay, so you know this form is plus a square, so I'll write with different color. Okay, plus a square plus a square. Okay, plus I'll write b square. Okay, and you have to find the inverse Laplace transform for this. Okay, you know it is into cos of bt, right? So that's what I have done. So this is like b square. Okay, and a is 3 by 2. Okay, just compare with this. And b square, if you take b is what, under root of 9 minus 3 by 2. Okay, so that's what I'm saying. So I'll write this. Okay, just comparing, this will be your frequency of oscillation, right? So frequency of oscillation is equal to root 9 minus 3 by 2 square. Okay, so just shall we, okay, 1 minus 2 square. Okay, so this you're writing 3 into 1 minus, again same thing. Okay, you know this was omega n into 1 minus eta square. Okay, same form, that's how. Okay, you'll get the same answer. So what was the answer? 2.6 radian per second you'll get. Okay, so if you want to go in the long way, you can get the frequency like this. Okay, by solving this equation y of t, but you don't have to solve for abc. Okay, because we are finding the, what will be the term, like frequency term. Okay, so that's why don't calculate abc. So this will be y of t. Okay, okay, so any doubt? But we know, right, we know this y of t equations already, that's derived in the lectures. Okay, you know what will be the unit step response for the second order system. Okay, and the frequency of oscillation will be omega d. Okay, damped frequency, and you know omega d is equal to omega into root of 1 minus eta square, and both values are already known to us. Okay, and you can get this. So this is the simplest, and again if you want to calculate the coefficients, go with this and just compare with the general equation. Okay, so any doubt in this question, question number 4? Again, this was very simple question. Okay, so we'll go to the next question. So rise time of the system given problem 2, rise time. So what is rise time? You know, pi minus beta by omega d. Okay, I hope this is correct formula. Okay, please interrupt me if this is wrong. Okay, so beta was, you know, cos of, I think cos of beta is theta. Okay, so beta. Okay, let me find out cos beta first. Beta value first. Okay, cos beta. So zeta is 0.5. Again, we calculated, I think, in this, yeah, previous question. So you know cos beta is equal to zeta, which is 0.5, and beta is cos inverse 0.5. Okay, so what is this value? Cos of 60 is equal to 0.5, right? So, but we have to write in radians, so pi by 3. Okay, which is equal to 60 degree. Okay, pi by 3. So pi minus pi by 3 by omega d. So omega d already, omega n, you can again you can do this. Okay, so its value is like, so what its value is 2 pi by 3 by, we have calculated previously 2.6. Okay, so this is like 2 into, you can do 3.14 by 2 into 3 into, I think 3 into 2.6. So what is this value? I think 0.8051. So you can write like 0.8 seconds. Okay, I hope you're getting the same answer. Okay, so to solve this, you have to know this formula, right? Rystrom formula and this. What is cos of beta, right? So in explain what is cos of beta. Okay, if you draw, so this is complex plane, right? This plane I'm writing. Okay, so you'll have two roots, right? This one. So this is what, minus zeta into omega, and this will be omega d, right? J omega d. This will be beta, right? And cos of beta is equal to what? Base, which is equal to this omega n by root of plus omega d square, right? Just omega n square minus, okay, if you write like this, omega n root of 1 minus zeta square whole square. Okay, if you do the whole square, you will get this. And this will get cancelled. So what you will be left with? Okay, so that's why this cos beta was this theta. Okay, but you have to know like what is this angle, right? So this is angle here like this. Okay, so this is, let me call this is S1 and S2. Okay, so S1 and S2 are roots of this S square plus 3S plus 9. Okay, so these are the roots. Any question? Very simple question. Rise time. Okay, sixth question will calculate the peak time of the system given in problem 2. Peak time you have to calculate again. So what is peak time here? You remember that will be pi minus omega t. Okay, so it depends on only one parameter, that is omega d, but it depends on natural frequency and the damping ratio. Okay, this is very simple. So what is omega d? I think 2.6, right? So this we already know, 3.14 pi 2.6. Okay, 1.2077. You can say this is peak time is 1.2 seconds. Okay, any doubt? Just we are using the formula and we're getting the answer, right? Derivations you already that's covered in lectures. So again, for the same transfer function, we have to find the maximum peak overshoot of the system. Okay, let's peak overshoot, okay, which is equal to e raised to power minus theta. Okay. Okay. So it's better you remember these formulas. Okay, it's very important in your questions also. Like in your exams, please remember these formulas. Okay, I hope this formula is correct. E raised to power minus theta into pi by 1 root of 1 minus theta square. Okay, so this will be in percentage. Okay, so everything is known. So this is 0.5 into 3. So this is 1 minus 0.5. Okay, so I think the formula, okay, I'm writing, I think somewhere I'm making mistake. Eta into pi, I think. Okay, just check the formula. I think 1 is eta into pi by root of 1 minus eta square into 100%. Okay, let me calculate this. Okay, in the chat box you can write whether this formula is correct or not. Okay, I'm just calculating with this. So 0.5, it is 0.75. Okay, so let me calculate the fraction here. 0.5 into 3.15 by root of 0.75. Okay, 1.8128. Can you confirm? Okay, let me just calculate this. E raised to power minus 1.8128. Okay, 0.1620. Okay, and we have to multiply by 100, right, to get in percentage. 16.20. Yeah, almost 16.3. The maximum overshoot of the system. Okay, yeah, everything is correct. Okay, so this is the overshoot. So if you draw this response y of t, okay, so this is 1. Okay, the response will be like this. Okay, so this value is like, so if you see what is the peak, this. Okay, so you can say if this is 1, so this is 1, so this green one will be like 1.1620, right? This is what it says, because we have calculated this as 16%, okay, or you can say it is 0.1620, okay, not in percentages. with respect to 1. Okay, so this is what is the overshoot. Okay, so maximum percent overshoot in percentage. Okay, so your y of t is the output, right? So any doubt in this question? Simple, you have to use this formula. Okay, everything is given. Only depends on zeta, right? When zeta is given as 0.5, and everything, if everything is correct, you will get 16.3. Okay, so I have calculated 0.2, but you will get this 16.3. Okay, and what it means is this. Okay, so in terms of absolute values, so I have drawn the waveform and I've shown you how the response is looking in terms of absolute value. Okay, so at infinity it will go to, okay, so y of t will become 1 at t tending to infinity, right? And in the first peak, so what will be its value? It will be 1.16. It will be 16.3% extra. Okay, so that's what it is. Okay, the setting time of the system given in problem 2 is, okay, for 2% error I will calculate. Okay, for 2% error back. Okay, so you know the formula, settling time is 4 by theta into omega, right? Okay, 0.5 into 3. Okay, this is 4 into 1.5. It's 2.66, I think. Yeah. Seconds, right? Okay, so let me draw like how it is. So this is 1, right? That's what we are, that's what we want our output to be. Okay, so it will, the output will achieve this. Okay, t equal to infinity. Okay. Okay, so we have set some band here, right? 5% band. So if this output reaches within this 5 or 2% band, okay, we say ki our output has reached its steady state. Okay, so this time period we have calculated just now. Okay, okay, so this is time period. Okay, for 2% I'm saying 2.66. So any doubt in this? Okay, which one of the following statement is true about a proportional controller? Okay, so proportional controller. So you know what is proportional controller if you write. So let me draw this is proportional controller and input is u e of s or et. So in terms of time, and this is ut, right? And what is there? What its gain? So let me call gs is gain. And for proportional controller, gs is equal to kp, right? Only a constant here. So this is constant gain. Okay. So let me not write g kp here. Okay. So you know u of t is equal to kp into et. Okay, if you take the Laplace transform, you'll get this kp into e of s. Okay, these two are important. So based on these, I'll answer this. The controller transfer function. So I'm reading out first statement. So to find out whether this statement is true or not. The controller transfer function is a complex variable. Okay, so this is the transfer function. Okay, it's just a constant, right? So it's just a constant value. It's not a complex variable. So the statement is false. Okay, second statement, it would lead to zero steady state error for all system while tracking a step reference input. So you have seen in the theory also. Okay, so this proportional controller will have a steady state error. Okay, so it will have a definite, like it will have a definite steady state error, not zero. So this is also wrong. So I think in the further weeks, further in the course, you'll see how the steady state error is non-zero if you are using this proportional controller. Okay. Because okay, let me say for the first order system. Okay, so let's see some system. First order system, it will be some constant. Let me say constant is a s plus let me say the pole is p. Okay, and you know the transfer function, how to calculate the closed loop transfer function. So controller transfer function is what? Kp. Okay, so it will be like this. Cs, and you have g of s, which is the Planck transfer function. So let's suppose we have taken this particular thing, first order system. So I don't know whether we'll get steady state error 0 or not. Let's check for this. Okay, so this is negative feedback and hs is equal to 1. Okay, for the closed loop transfer function, what you'll get, kp into a is plus p plus a into kp. Okay, let me not directly write. Oh, I'll write this. So this, if you combine, okay, what you'll get. So let me write this as this. I'll write as not gs. I'll write ps. Okay, so this is ps, and the combined one will be equal to gs. You know, gs will be equal to a into kp by s plus p. Okay, so let me just replace a with some variables like 2. Okay, and let's say this is, okay, let's say this is 4, and let's say kp is again let me take a variable, let's say it's 100. Okay, real values, all real values. Okay, so a is 2 into 100 is plus 4. Okay, something like that, just arbitrary value. So what is, so this is 3 of s. So you know, closed loop transfer function is this, right? Okay, so 2 into 100. Okay, this is s plus 4. So what you'll get, 1 plus 2 into 100 is plus 4. Okay, if you simplify, you'll get 200, or let me write like this, 2 into 100 is plus 4 into 2 into 100, right? This you'll get closed loop transfer function. Okay, if you're trying to find the steady state value, so what you'll get, just closed loop, and for the, 1 second, I'll just add on the page. Okay, say find steady state output for unit step, right? So what you will get, this is your y of s or y of s by rs, right? Rs is your, so this is not required, this additional I am doing. Okay, unit step. Okay, so ys will be closed loop transfer function, whatever this 200 is plus 4 plus 2 into 100 into u of s. Okay, u of s, so I'm just replacing with 1 by s. Okay, unit step means you'll get u of s is 1 by s, right? So this is 1, just remember this. Okay, your output should be 1. Okay, I think here you'll get 1 if you apply final value theorem. So what is that value? S into 2 into 100. Okay, if you put a limit, so what you will get? So put the limit 2 into 100. Okay, so only this term will be equal to 0. So you'll be left with 4. Okay, change the color. 4 plus 2 into 100, right? Okay, so if you exactly calculate, this is 200 and this is 204. Okay, this will be slightly less than 1, right? Your output, if you see, this is limit t tending to infinity y of t, right? You're finding the steady state value. Okay, which is, so to be more precise, let me calculate the value. So this is 200 by 204. Okay, something like 0.980. Okay, let me take 0.98. Okay, so I like 0.98. Okay, so how the response will be? Okay, so your output should be equal to 1. Okay, but your input will be like this. So this is all approximate drawing. Okay, so at steady state, this will be like this. So this will be 0.98 and this will be equal to 1. Okay, so this is the steady state. Okay, 1 minus 0.98. Okay, yeah, this is 0.02, right? So this is the steady state error. Okay, so that's what I'm saying. For a particular system and input, this proportional controller will have non-zero steady state error. Okay, so this is wrong for all system. It will not be there. If I change the system, we'll get 0 error. Okay, so that's why. Just I'll just shown you with an example. So you'll study this in further in the course. Okay, let me see the third statement. The control input is inversely proportional to the error. So you see this statement. Okay, so control input is inversely proportional to the error. So you see E of P is proportional or inversely proportional to error. So it is proportional to error, right? So this statement is also wrong. So it says inversely, but that is the control input. This is the control input, right? Control input means your control. Okay, so if you see the system where I've drawn the system, okay, this system. So this is U of S, right? Okay, so this is controlled input, right, to the plant. So that's what it's saying, controlled input. Okay, so that's what. Yeah, here. So this is controlled input, which is directly proportional to E of t. Okay, the statement is also false. The control input at an instant of time is dependent only on the value of error at that instant of time. Okay, so you see this is correct, right? Kp is just a constant value. So at any instant of time, it depends on the current value of E, right? Okay, so this statement is correct. Only on the value of error at that instant of time. Okay, if you see this equation. So any doubt in this? This is also simple. So this statement 3, the control input, sorry, statement 2, it would lead to zero steady state error for all system while tracking a step reference input. So we'll see like further in the course how a non-zero steady state error will be there. Okay, so I've just shown you with an example. Okay, for the first order system. So let's go into the question 10. Okay, consider a second order system that is governed by equation. It is again you have to find out whether system is what, stable, unstable, critically stable, and marginally stable. Okay, let me write the equation. This 1 by s square plus s plus 1. Okay, this is the transfer function we are getting. So just by finding out the roots we can find out. So this is not s square plus s plus 1. Okay, so this is the characteristic equation, right? Just by looking at this characteristic equation, you can find out whether the system is what, stable or not. Okay, because if all the roots of this characteristic equations are poles of this particular transfer function is lying on the left hand side of the complex plane, we'll say the system is stable. Okay, so find the roots of this equation. The roots of this equation will be what? Poles, right? So this will be okay. So what you'll get this one as the roots are like this. Somewhere here, this is S1 and this is S2, right? How we can say it's lying in the left hand side, because you see the real part minus 1 by 2. Okay, so this will be S1 and this will be S2. Okay, so what can we say about the system? Critically stable, unstable, marginally stable. Okay, other okay, let me okay, please answer in the chat box. Other thing also, we can, what we can do is, we know this, it's a second order system, right? You can compare with this also, right? This is the general second order, like characteristic equation of second order system. Okay, you can know omega n will be equal to 1, and this 2 into zeta into omega n is also equal to 1. Okay, omega n is 1, omega is 1 by 2. Okay, from here itself you can tell. So two things we can find out. Okay, first, both the poles are lying in this plane, right? So, and they're not lying on the imaginary axis, right? So what can we say? Left hand side. Okay, so what can you say? The system is stable or not?
Stable.
Correct. Okay, so it's just a second order system, but finding the poles, you know, where the location of poles are, right? Okay, location of poles are in the left hand side, though it's like you're also having the imaginary part, okay, but it's not on the imaginary axis, right? So you cannot say, so let's suppose for a particular transfer function we have roots here like this, okay, then you'll say the system is marginally stable, right? Okay, but that is not the case here. Okay, okay, for what is happening critically stable, if you have pole at zero origin, okay, then you say it's critically stable. I think this type of questions are already covered in the previous tutorial also. I think you'll have no doubt in this. Okay, just find the pole, see the location where they are. If they are lying in the left hand side, we say the system is stable. Simple. Okay. Unity negative feedback closed loop control system is designed with the above system plan described in problem 10. Okay, using a proportional controller with Kp being the proportional gain, the closed loop system is stable for all. So we have to find out whether the, for what value of Kp the closed loop system is stable. Okay, so this is the controller and plant is given in question number 10 like this. This is the plant. Okay. For the unity feedback like this. This is y of s, and you know this is unit step. Okay, hs is equal to 1. Okay, now we write hs is equal to 1, and this is plant, this is controller. Okay, so again, unity negative feedback and closed loop system is designed with the above plant described in problem 10 using proportional controller. The closed loop system is stable. You have to find out closed loop transfer function. Okay, so let us find the closed loop transfer function. Okay, so you used to say this is cs and this is ps, right? And you know, to find out closed loop transfer function, first you have to find gs, which is cs into ps. Okay, which will be equal to kp. Okay, let me write here. Okay, kp into s square plus s plus 1. Then what is closed loop transfer function? Gs by 1 plus Gs. Okay, so square plus s plus 1. Okay, so finally kp by s square plus s plus 1 plus kp. Okay, closed loop transfer function, okay, which is y of s by r of s is equal to kp by square plus s plus 1 plus kp. 1 plus kp is the constant term. Okay, like this. Okay, so you have to find out closed loop system is stable. When the closed loop system is stable, when poles of this equation, okay, poles of the characteristic equation lie in left hand side of complex plane of S plane, right? So you have to ensure the poles of this transfer function lie in left hand side of S plane, okay, by seeing what is the possible value of Kp. Okay, that's what we want. Okay, so we'll work on this characteristic equation, which is s square plus 2, I think s, okay, s square plus s plus 1 plus Kp. Okay, so this is the characteristic equation. So what is the possibility, right? So let me first find the roots. Okay, plus minus 1 square minus 4 AC by 2. Okay, so this will be S1 and S2 will be right, minus 1 plus KP. This is 2, and again S2 will be minus 1 minus 1 plus minus 4 1 plus KP. Okay, these are the two roots. Okay, and both these roots should lie in the left hand side. Okay, so but one thing is very clear. Okay, so real part, right? This part. So what is happening? This real part, it's negative, right? Minus 1 by 2. Okay, let me plot the S plane first. Okay, so these are two roots, right? So we have different possibilities based on the second part, right? So second part can be positive, like it can be imaginary and it can be real, right? Second part. So we have to see what value of Kp it is lying in the left hand side. Okay, so let's assume for let's first see for what value of Kp the roots are imaginary. Okay, because we know the real part is already negative, and if the second part, okay, this part is, okay, let me write do one more step and explain. Okay, so S is, so I'm writing minus 1 by 2 plus minus root of 1 minus 4 1 plus Kp by 2. Okay, so this is part 1 of S and this is part 2, right? Okay, so what I'm saying, so let the part 2 be imaginary. Okay, so first case, let part 2 be imaginary. So what will happen if part 2 is imaginary? You see, the real part 1 is the real part, right? This one. So this is the real part. So your poles will be lying like this. Somewhere this is -1/2. Okay. So along this line. So your poles will be along this line, right? So it can be here. Okay. It can be here also, depending on what value of Kp you choose. Okay. So along this line, you'll get. And what we can say about the system is stable, right? Because your poles will be lying in the left hand side, right? So this is the case one, like this possibility can be can occur, right? So the part 2 should be imaginary. So what value of Kp the part 2 is imaginary? Let's see. Okay. So for this to be imaginary, what is happening? This should be less than 0, right? Okay. Because the term which is in the root, if that is imaginary, sorry, that is negative, then we'll have the J part, right? So that's what I'm doing here. So any doubt up to here, this question? Okay, let me see, all the roots are taken care. Yeah, and -4. This is okay. What will be its value? This will be 4 by this. And okay, let me write this. Kp is greater than -3/4. Okay. If your Kp is greater than -3/4, then this will be imaginary. Okay, if that is imaginary, then roots will be lying like this. Okay, the locus of roots will be along this line. Okay, and then we will say the system is okay, stable, right? This is one possibility, right? Any doubt? Okay, just here finding the possibility. Okay, let's take another case also. Case 2. Case 2, what is happening? So what can happen is this, uh, the value which is in the root, okay, it's not negative. It is, what do you say? It's greater than 0, right? It's greater than 0. So let me again write this term. So this is the case. And so S1 and S2 are real. Okay, so there is no imaginary part. Okay, so again, if I draw this, okay, so what are the possibility if S1 and S2 are real? One possibility is S1 and S2 lie like this, right? If they lie like this, we'll say the system is stable. Other possibility is what? The system is, this poles are lying like this. And if one of the pole is lying in the right hand side, then we'll say the system is unstable. Okay, so there are two possibilities here also. So we want to find the possibility for this one. Both the roots lie in the left hand side. Okay, so this is imaginary, this is real. Okay, so what should be the value of that Kp again? Okay, just see. Okay, so that you under root 1 plus, sorry, this is 1 minus 4, 1 plus kp, okay, should be less than 1, right? Let's take the magnitude here, okay? It will be more clear if I write like this, okay? So one part, okay, see, we have already written part 1 and part 2. We are just comparing part 1 and part 2. Since the denominator is same, I am comparing the numerator, okay? Part 1 and part 2, you see here. So this is part 1 and part 2 is this. Since the denominator is same, I am comparing the numerator, okay? So we want this, okay. So let me put minus here, yeah. This is part 1 and this is part 2, okay? And what we want is system to be like this. This should be S1 more negative than S2, right? This, let me call this as plus, okay? So you want this scenario also where the system is stable if the roots are lying like this, okay? For that, what should happen? Okay, the second part should be less than first part, right? In magnitude, okay? You have to see this, okay? Let me give you example. If minus 1 plus you say 0.5, okay, by 2, again this will be what? Negative, right? If suppose the root part is greater than minus 1, let's say 2, so what will happen? Positive, right? This we don't want, right? This we don't want, okay? So that's why I'm comparing this second part with the first part like this. It should be less than 1, okay? So let's compare what we'll get. You'll see, or we can say 1 minus 4 1 plus kp less than 1, okay? So what you'll get, minus, this will be minus 4 kp less than 0, okay? Minus 1, okay? So let me explain this step. Okay, it's very simple. So I know, so because I'm saying the root of under root of this value is less than 1, okay? So can I write this? Very simple. You can square also, no problem. You will get the same value, okay? So kp, finally I'm getting kp is greater than 1, okay? So I have to combine both the cases, case 1 and case 2, okay? So if you plot kp, okay, single kp, so it is 0 and this is 0.3 by 4. So the first case says my value of kp should be greater than, okay, minus 3 by 4, and its second one says, if I draw kp, this is 0, this is minus 1, okay, this is somewhere here, it will be minus 3 by 4, I think, okay? So this is, okay, so this is the plot for second, so this is kp, right? Okay, so you have to take the union of these two, right? if kp is greater than -1, roots are lying like this. Okay, if kp is greater than -3/4, again we'll go to the case 1 where the roots will be going to the imaginary axis. So in both the cases we'll have roots on the left hand side. Okay, so we'll say if kp is greater than -1, okay, so what they have asked is this loop system is stable. If kp is greater than -1/2, poles lie in left hand side of complex plane. Okay, hence the system is stable. Closed loop system is stable. Okay, okay. So what is the answer for this? Kp is greater than -1. So any doubt? Okay, we are just seeing the cases. Just take the characteristic equation, okay? And for what value of Kp, okay, roots lie on the left hand side. Okay, so I've taken one case where the part 2 is imaginary. Okay, so if the part 2 is imaginary, how to ensure part 2 is imaginary? The thing that is the value under root is negative, right? So I'm getting Kp is greater than -3/4. If kp is greater than -3/4, my roots will be lying in the my roots will be imaginary. Okay, real part will be negative and imaginary part. Okay, will be having, but roots will be lying in the left hand plane. Again, we have to see a situation where if the part 2 is not imaginary, right? But we have to ensure that part 2 is, or this S1 and S2 are real. So S1 and S2 both should be negative. Okay, so to satisfy that, we have this condition. And from that we got kp is greater than -1. Okay, so if we take kp greater than -1, we'll ensure that roots or the poles will always lie in left hand side. Okay, so any doubt? Okay, you tried with yourself. Okay, just make the cases. Okay, we'll go to the next question then. The closed loop system designed in problem 11 is expected to track a unit step reference input. The steady state tracking error is. Okay, so y of s by r of s. Closed loop transfer function is kp by s square plus s plus kp, 1 plus kp. Okay, so this is the closed loop transfer function. Okay, from the previous question. So this one. Okay, so I'm just writing closed loop transfer function gs 1 plus gs. Okay, so this is like this. Okay, okay, for a step unit step reference input. Okay, so rs is unit step, which is equal to 1 by s. Okay, the steady state tracking error. Okay, so basically this, so this is 1 and your output should be, so let's assume like it will be like this, and you'll have some. Okay, so let me change this color. You'll be something will be there, and you'll have some steady state error. Okay, for this particular system. So the steady state error we want to find out. Okay, so y of s we want to find out, which is equal to kp s square plus s plus 1 plus kp into 1 by s, right? and we want to find out the steady state value of y of s. Okay, so use the final value theorem. This is infinity. Okay, so you will get y of t. So say how to get s tends to 0, s into kp s square plus s plus 1 plus kp into 1 by s. Okay, so this gets cancelled, just put the limit. So it will get kp by 1 plus kp. Okay, so this is the steady state value for unit step input. Okay, and what we have to find out the steady state tracking error, right? So what is error? There will be 1 minus kp 1 plus kp because it's not going to 1. Okay, so there will be a steady state error. So what is that steady state error? 1 by 1 plus kp. Okay, this one, first one is correct. Okay, any doubt in this? So you have to find the steady state value of y of s. Okay, so I used a simple final value theorem to find out. Okay, so steady state value is kp by 1 plus kp. Okay, but due to this, it's not reaching 1, right? 1 should be its value, but it's not reaching value. Sorry, 1. So there will be always a error. So that's what the error is. 1 minus the steady state value will get the error. Okay. Next question. Which one of the following statement is true about the integral controller? Okay, what is integral controller? U of s is U of s by s. Okay, this is the transfer function. The controller transfer function introduces an open loop 0 at 0. Okay, this is wrong because it introduces, it has what? Open loop pole at 0. I'll say origin, just not to get confused with 0. Okay, open loop pole at origin. Okay, so this is wrong, right? Controller transfer function introduces open loop 0. No, it introduces open loop pole at 0. Okay, it would always lead to non-zero steady state error while tracking a step reference input. This is also wrong. Integral error will lead to zero steady state error. So I'm not doing that, but it is there. Like I think in lecture notes also, and in the further in the course if we study, we will find out. Okay, so it will lead to zero steady state error. So this statement is also wrong. So it can lead to actuator saturation. This is true because if you write in terms of time, what you'll get. So you'll get. Sorry, I'm not. This is actually transfer function is ki by s into es, or yeah. So ki, okay, 0 to t e tau d tau. Okay, you are integrating error over time, right? Okay, so this is ut, right? And since you are integrating means you are summing all the errors, and it may reach a point where the summation of this is like the summation of this will be reaching to saturation, like ut will reach saturation limit. Okay, so ut saturation. Okay, it will reach saturation because of this summation of error. So that can happen. It can lead to actuator saturation because after controller, actuator will be there. That will be driving the plant. Okay, so that can happen. So the control input at any instant of time depends only on current value of the error. So this is wrong, right? It depends on past also because we are integrating. Straightforward, this is wrong. Okay, only third option is correct. Okay, 14th will go. Which one of the following statement is true about a derivative controller? What is derivative controller? KD. Okay, S. S into E of S. Okay, so this is the transfer function. The controller transfer function introduces open loop pole. No, it introduces open loop 0 at origin. Okay, this is wrong. It would provide a non-zero control input in the presence of non-zero constant error signal. Okay, this let me write in terms of, so this will be d e of t by dt. Okay, non-zero control input in the presence of non-zero error. So if you're, that is not true. Okay, so this value can be zero, right? This value can be zero, but your e of t is not zero. Okay, if e of t is not zero, what can happen? Your d by e of t can be zero, right? Can be zero, and because of that your u of t will be zero. Okay, so for non-zero error you're getting what? Zero u of t control input. So this statement is also wrong, right? It would provide a, it can provide a zero control input in the presence of non-zero constant error. Okay, constant means error is constant, that's why it's non-zero. Okay, so I'll write e of t is non-zero constant value, constant. Okay, so E of t is constant anyway, d by dt of that will be equal to 0, but U of t will be equal to 0. Okay, so this statement is also false. You can get zero control input. Okay, it is anticipatory in nature. This is also true. This is the only thing that is true, anticipatory, because of what? It is also anticipating the future. Okay, fourth statement, the control input at an instant of time depends solely on the past values. No, because derivative term is there. Okay, so previous integral controller depends on past value, it depends on future also, d by d. Okay, this statement is false. Okay, because you are finding the slope at every moment. Okay, so it is giving us the future also. Okay, so last I will do quickly. Consider a second order system that is governed by this equation. A unity negative feedback closed loop control system is designed for system. The closed loop system would be stabilized by, okay, we got to find out one by one. For this particular transfer function, let me find the transfer function first. Let me write u. Okay, s square y of s minus 2 y of s equal to u of s. So what is y of s? U of s divided by s square minus 2. So if you see this transfer function, this is unstable, right? Because what is, you see the roots. Okay, so its roots are lying in left hand, right hand side. So this is anyway, this is unstable. Okay, but we have to stabilize this system by using any appropriate controller. So how to find out? Okay, so let's do one by one. So its roots you can write here, plus root 2 and minus root 2. Okay, so you can say this pole in right hand side of S plane. Okay, that's why the system is unstable. Sorry, yeah, unstable. So using proportional controller, okay, so I'll write u of s, you know, which is equal to kp by, sorry, kp into e of s. Okay, so I'll directly write open loop transfer function. So which is GS. Okay. Okay, let me. So what we are doing is this is controller. So C of S. Okay, and the system is given, the plant is given to me. So this is how closed loop system is. Okay, we have to choose appropriate controller so as to stabilize the system. Okay, which controller can stabilize? CS you have to choose. Okay, and CS is what? So in case of first, proportional controller. Okay, you know CS transfer function is equal to just KP. Okay, which is equal to what? US by, because you know here you will get U of S, here you will get E of S. Okay, that's why U of S by E of S. U of S by E of S is equal to KP. Okay, so what is open loop transfer function? Not let me write this as, you know, this will be GSS, right? So G. So G of S will be KP into the plant transfer function. Okay, now let's find the closed loop transfer function. So the closed loop transfer function be GS1 plus GS. Okay, so it will be KP. So directly I am writing it. Okay, square minus 2 plus KP. Okay, so this is KP square plus KP minus 2. So you know, if you plot this, okay, KP minus 2. So what is happening? If KP minus 2, let's suppose it's greater than 0. So what is happening? KP is greater than 2. So this is for what condition? For marginally stable condition. Okay. Okay, and what will happen if I reduce KP? If other condition is KP minus 2 is less than 0. So KP is less than 2. So in this case, what will happen? This will become negative, right? So you just have to focus on this part. Okay. In one condition, when KP minus 2 is positive, what is happening? So in the, okay, let me say this as case 1. And this is case 2, right? So in case 1, what is happening? Your poles are lying like this. Okay, S square plus something, right? So you'll say the system is marginally stable, marginally stable. Okay, but in case of case 2, what is happening? Your poles are lying lie like this. Okay, KP, no, it will lie. I think, yeah, it's like S square minus 2. Okay, so your roots will be like this. S1, this is S2 again, S1, S2. Okay, so for this case, second case, we'll say the system is unstable, right? System. Okay, so the proportional controller won't work. So KP, if you just put a proportional controller, you won't be able to stabilize the system. Okay, either it will be marginally stable, that we don't want, right? It can be unstable also because it's anyway approximate modeling. Okay, that already we have covered in the lecture. And other is it's already unstable. So in both the cases, it's unstable. Okay, if we go for the second type of controller, what is that second type of controller? Integral controller. So I'll just do it quickly. We don't have time. Okay, if we take the integral controller, okay, so its transfer function is equal to ki by s. Okay, ki is the gain. Okay, so what is gs? Gs would be equal to ki into s square minus 2. Okay, so closed loop transfer function will be gs by 1 plus gs. So directly I'll write ki, so s square, so this will be square minus 2 plus k. Okay, if you write it, it will be ki by s cube minus 2s plus k. Okay, so you have to find the roots of this. Okay, but this is quadratic. Okay, so you'll see in the next classes by using Horvitz criteria. Okay, so this particular will be for this particular coefficient, because one of the coefficient is negative minus 2. Okay, so this will be, or you can say one pole will lie in right hand side. So I'm not doing that analysis. Okay, so we'll study in the next week. Okay, why this will be unstable. So I'm just directly writing one pole will lie in RHS. So that's why this unstable system. Okay, so the closed loop transfer function will be unstable. Okay, so this integral controller is also not working. So let us see with the third type of controller, that is derivative controller. Okay, so derivative controller, what is that? C of s is kd into s. Okay, kd into s. Okay, so what is c of s? S into kd by s square minus 2. And what is closed loop transfer function? S into kd by s square. Directly I'm writing plus s into kd. So which you can directly write s into kd, okay, s square plus s into kd minus 2. Okay, so directly from here also, like if you apply the Horvitz criteria, okay, that we'll see in the next, because time is not there, otherwise you can find the roots. What I can say is find the roots and find the values of kp, okay, kd. Okay, so you'll see that for particular value of kd it will be unstable. Okay, so just by looking at this equation also, because we'll study in the next classes, this is if you find the root. Okay, so the roots, because it's having this negative, because of this negative, okay, let me just say because of this negative, I'm directly writing, you can find the roots also. Okay, the closed loop system is transfer function is unstable because of this minus 2. Okay, so if you use the last part, proportional derivative controller. Okay, so the CS will be Kp plus S into Kd, right? We are just adding these two controllers, and G of S will be Kp plus S into Kd s square minus 2 if you find the closed loop transfer function, you'll get kp plus s into kd by s square minus 2 plus kp plus s into kd. If you just arrange it properly, you'll get s square plus s into kd, okay, plus kp minus 2. Okay, this is the characteristic equation. Okay, so we have to find out. So let me find out whether the roots are, for what value of kd the system is stable or not. Okay, so this is the characteristic equation, right? Its roots are poles and those poles should lie on the left hand side. Okay, so finding the roots, so minus kd plus minus kd square minus 4 kp minus 2, okay, by 2. You have to see from here. Okay, from roots, if we apply that criteria, it will be very easy. But from the roots, you can see here. Okay, first is okay. What you can see is KD case 1, I'll say KD is greater than 0. Okay, let's assume KD is greater than 0. And let's assume this condition. Okay, let's assume this condition where the roots are lying here like this. Okay, you are also having the imaginary part. Real part is negative because real part is what? KD. S is here minus KD by 2 plus minus this KD square minus 4 KP minus, sorry, not keep, okay, KP is coming into picture. KP minus 2. Okay, by 2. So I said KD is greater than 0, right? So this part, this is negative, right? KD is greater than 0. You can say KD as 4. So minus 4 by 2 is minus 2, right? Minus 2 is what? Real, negative real. So that's why I want this second part to be imaginary. Okay. So if this is what I think, I'll get the poles like this that I have drawn. Okay. So I can say the system is stable, right? Because it is lying in left hand side. So for that, what I have to do, KD is greater than 0 and it also KD square minus 4 KP minus 2 is less than 0, right? I want this to be imaginary. So KD square is 4 KP minus 2. Okay, so if I try to find what is the value of KP, what I'll get KD by 4 plus 4K plus 2. So what I'm getting, this is positive, right? KD square plus 4 plus 2. This will be anyway positive. So KP is also positive. Okay. So system is stable. Like if I draw KD versus KP, okay. If I draw KD versus KP, I'm getting something like this. So this is KD and this is KP. Okay, let's suppose if KD is greater than, KP is greater than this value. Let me call this as some value A. So it will be like if KB and KD values are in this region, you can say the system is stable, right? The system is stable. Okay, because of this, the roots, I'll say the poles are lying in left hand side. Okay, complex plane with imaginary parts. Okay, with imaginary part. Okay, why I'm saying imaginary part? Because I've done this KD square minus this, if you see equation. Okay, this is the case 1, right? So other cases can also happen. Okay, so other case is what? It is second case. What can happen is, okay, let me write equation again, the roots KD by 2 plus minus root of KD square minus 4 KP minus 2 by 2. Okay. So other thing is what can happen is this is again I will say KD is greater than 0. Okay, because what I want is this. Now I want this situation. Both the roots are lying like this. Okay, for that KD has to be greater than 0. Okay, if it is less than 0, then that's other point. And what can I say is the other part. So if I say this KD square minus 4 KP minus 2, okay, if this is less than this part, KD part, okay, I'm just comparing magnitude. This also is one possibility, okay. Then you'll have, because, okay, let me write again the same thing we have done for the previous one also. Minus KD by 2, one root will be again minus KD square minus 4 KP minus 2. Okay, this will be one root, other root will be S2 minus KD by 2 plus KD square minus 4 KP minus 2 by 2. And I want these roots to be like this, S1 and S2. Okay, and I have to be more careful with this. Okay, because it should lie in the left hand side. So what I have to do, so this part 2, so this is part 2, this part 1. Okay, so this part 2 has to be less than part 1, right? Then only it will be negative. Summation of negative and positive value, if negative is more, then it overall the summation will be negative, right? That's what I'm doing. Okay, so just comparing these two values. So this KD square minus 4 KP minus 2 and KD value. Okay, so I'm saying this is greater because the denominator is 2 only. Okay, just squaring what you will get, square minus KP minus 2 KD square. Okay, so I think this will get cancelled. KP is 4 KP. Okay, so we can say this is 2 KP. So what we can write, KP is greater than 2 here. So if KP is greater than 2, so what we can say, it will be situation like this. Then also the system is stable, right? Yeah. KD is greater than 0 in both the cases. See, case 1, KD is greater than 0 and KP is greater than this value. And in the second case, KP is greater than 2. Okay, let me plot this also. Okay, so I have plotted KD here and KP here. So KD and this is KP. So for KP greater than 2, so this, okay, so system will be stable. For these values of KP and KD. Okay, so this is detailed analysis. So it just asked like what, just you have to find out the closed loop system would be stabilized. Okay, so you know this, it would be stabilized for proportional derivative control. Okay, so we have seen for what values of KP and KD it can be stabilized in detail, right? You can do the analysis also. So any doubt in this question? So any doubt? Once we study Raoult-Harvitz criteria, it will be more clear. Directly we can tell, okay, by seeing the coefficients. Okay, thank you. So any doubt for this today's lecture? Okay, I think we are You exceeded the time limit. Okay, so I'll
Thank
upload the
you.
lecture. Thank you for attending this lecture. Okay, so any doubt? Okay, so I'll see you on Tuesday. Okay, next Tuesday. So we'll be covering questions based on week 5. Okay, so I'll upload these notes and lecture this live session. Okay, so thank you for attending the session. Thank you very much. I'll see you in the next session.
Thank you.
Thank you. Okay, first answer. Okay, first answer. Go to the first answer. This one you're saying? A second order system is governed by this? Or which answer? Like first answer is I think okay. Be specific, like which question number? Because I think question number 1 is very straightforward. Or you're saying the last part? You're saying the last question? Okay. I think if I first part, okay, you can write like which part, like which question. If you're asking me first question, second order system, okay, this is very simple question. You have to find the roots. Simple, yeah. Or you can find zeta, and zeta is coming out to be greater than 1. That's why we said the system is overdam system. Okay, simple. You can find the roots also, and both the roots will be real negative. So that's why you can say from that analysis also you can say the system is overdam system. Okay, so I'm not getting any feedback like which. Okay, then I think. Okay, then I'll see you in the next session. Thank you for attending the session. Thank you.